So this is the third video on the aldol reaction, and this is actually when we get into the actual aldol reaction, which really is what we call an aldol addition reaction. So in this case, the product is actually going to be what we call a beta hydroxyaldehyde or ketone in that fashion. And so we're going to use this enolate that we formed to actually add to something else or another aldehyde or ketone. And so sort of the name breaks down. The ald part is for the aldehyde that we have. That's going to actually sort of add to this. And the all is the actual alcohol that's formed from the addition from the carbonyl that we're going to see. So this gives us the alcohol. And this all kind of combines to the aldol reaction. Okay, so for this, if I were to take two equivalents of this aldehyde and treat this with base, so let's just use sodium hydroxide here at this point. Of course, I would form the enolate, and then that enolate would then add to another one of these aldehydes. So here you can see the two portions that we are generating. And so that's the overall reaction there that we see. So what's happening here at this point? How does this work? Well, what's happening first is we're going to need to generate our enolate. So here's our base. We're going to use sodium hydroxide. And of course, we're going to form this enolate by deprotonation of one of these alpha hydrogens, giving us the enolate. I'm just going to kind of flip it around here. And so you can see now we've got the enolate there, and then we have another equivalent of the aldehyde that we had originally. And the enolate here can kick back in and then go and add to the carbonyl carbon, just like it adds to any other electrophile that we've seen in this series. And then once we get to this point, we've got some water that's left over from the base as it had abstracted the proton, and this guy can come over here and get protonated. We reform our base or our catalyst at this point. And there you go. You now have your beta hydroxyaldehyde. Notice that it's beta because it's one away from the alpha carbon is the OH. So now we've added this there. Now notice that this can also happen with ketones, but you have to remember that ketones themselves are a little bit less reactive than aldehydes. And the reason being is that aldehydes don't have the extra R group that's on there, so they have a less sort of donating to that carbonyl group. So ketones tend to react a little bit more slowly in this regard. But just keep that in mind, that ketones, of course, do this as well.
I'm fine, thank you. I'm getting ready to study.
Okay, so aldol condensation is sort of another term that happens within sort of an extension of this reaction. And it is more or less when the product of the aldol addition that you have, that OH there, is going to actually dehydrate. So you're going to lose a molecule of water. And when this happens, when you lose this molecule of water, you form what we call an alpha beta unsaturated aldehyde or ketone.
She got mad at me and yelled at me, and I pissed in my pants. And I never did change my pee pants all day.
Now, one thing that you kind of, just as far as terminology goes, for condensation reactions, what these actually do, or what they kind of mean, is that you're going to, in a sense, you're going to combine two things or two molecules, and you're going to combine them with the loss of some other small molecule. So in this case, when we're talking about aldol condensation reactions, we're combining two molecules and then we're losing a molecule of water. So water in this case is our sort of small molecule that we're losing. So let me just give you an example. So we're going to go back through the same aldol reaction that we did previously. So I'm going to just draw in my hydrogens here. And here you can see that we have this base that's going to form our enolate again. And now, once I draw in this enolate that we've formed, we're going to attack another molecule of the same aldehyde that we have, because we've got two equivalents there. And as we draw our products here, we can see here with our aldol addition, and this guy right here gets protonated. We're going to reform our base catalyst here. And now I've got this OH that's kind of hanging out there, and I've still got base that's in there. And so if I increase the temperature, put some heat in there. So I'm going to put this in red. Heat here is the sort of important factor here in this case, and we're going to eliminate this. And what we see is that we actually get a double bond, and you can think about this as sort of a thermodynamic product, in that we're actually putting a double bond in there that is in conjugation with the carbonyl, and so that's thermodynamically more stable. However, the way that I have it drawn is not exactly the best mechanism for this. So a better mechanism for this elimination, if you think back to Organic 1, is the E1CB mechanism. And let me just show you what this guy looks like. So here's the product of the aldol reaction that we did, the aldol addition. This guy's going to eliminate get rid of our hydrogen that's here, and we're going to put this negative charge that's right there on the alpha carbon. And what you notice is that I can draw a resonance structure for this that goes, and the negative charge can reside here on this oxygen. And you can see that here. And then when it kicks back in, it can actually kick out my leaving group. And so this is sort of E1CB. That's the designated mechanism for this. The sort of aspect that's important here is that you've got to have this stabilizing group. So notice that we've eliminated that OH minus. We didn't do it directly. This is sort of a better mechanism for that. And so the E1CB requires that you have a stabilizing group that's adjacent to the charge, and you can see that there, that we have this carbonyl that we can resonate with. And so we have to have this sort of stabilization that you see there, right at this point. Okay, the next aspect or part of this that we need to talk about is the crossed aldol reaction. So what if I'm using two different carbonyl compounds that both have alpha hydrogens? And if you think about this, when I have two different carbonyl compounds that both have alpha hydrogens, then that means that I can actually get a mixture of 4 different products. And if I'm going to get a mixture of 4 different products, well, then this reaction really isn't quite useful at all. So the idea is that I want to be able to control whether or not I get one product, right?
Can you bring me my chapstick?
No, Napoleon.
But my lips hurt real bad.
So you can sort of affect this if you use something that as an aldehyde that has no enolizable protons, and then another one that has only one set of enolizable protons. So if only one of your reactants has one set of enolizable protons, then you're golden, and what that means is that you won't get this huge mixture. The thing is, though, is that you are going to need to add this guy slowly because you don't want it to self-add to it, to itself. So this can lead to only giving you only one product. So here's an example. So here is an aldehyde, benzaldehyde, with no alpha hydrogens. And then we have acetaldehyde here that has only one set of alpha hydrogens. So if I treat this with base, then I form, of course, the enolate from the acetaldehyde. I'm going to add to my benzaldehyde, and I'm going to form this guy here. Now, if I added a little bit of heat to this, I'm going to very quickly eliminate. And one of the things that you kind of look for in whether or not it eliminates or not is this increase in conjugation. So you can see that I've got this benzene ring, and then I've got the aldehyde. And so this probably would eliminate more or less without having any real major addition of heat as well. What if both of the guys that I'm using here have enolizable protons? Then what I need to do is I want to completely enolize one of them, and I'm going to use LDA to do this. So here's my example. I'm going to take cyclopentanone. Going to form the enolate completely with cyclopentanone. And then I'm going to take the other guy that I'm going to use. Even though it has these enolizable protons, you can see to the right of the aldehyde, I'm going to add this guy very slowly. So what I'm looking for is I'm actually going to get addition to the aldehyde first, as opposed to having it actually deprotonate any of the alpha hydrogens. So now I can form this product pretty securely without having to worry about getting a mixture of products. So the idea is that we want to completely enolize the first carbonyl, right, with using LDA, and then once that's done, then add slowly the other carbonyl that I wanted to add to. And so then this way you can kind of control it, and you can make sure that you don't actually get a mixture of products. Alright, so now we have the claisen, and it's spelled clausen up there, but you should note that it should be CLAISEN. That's that daggum autocorrect. And this is when two molecules of an ester basically add together, just like in sort of the aldol reaction, that they add together and they undergo this sort of similar type of condensation reaction.
Stop! That's perfect.
So let me just give you an example of this. So here's our ester, and you can see to the left of the carbonyl I've got an enolizable proton, and I'm going to treat this guy here with base, and I'm going to deprotonate this, and then when I'm done I'm going to acidify everything to neutralize my reaction conditions. And so if I have more than one equivalent of my ester there, you can see that I'm going to form this product. And you can see that the product here is a little bit different. Notice that I have alpha and beta that are adjacent to this ketone that's on the right. And so what I see is that I actually form an alpha-beta ketone, or ketoester actually. And then the other thing that I want to point out to you is notice the base. You see the base I'm using? It's the same as if it were the alcohol part of the ester. And this is done just in case if it were to hydrolyze the ester, well then I'd have the same product, right? Because I'm still be adding this methoxide again. And so I have an OCH3 that's there, and so therefore it wouldn't do anything. So you always want to make sure that you use the same sort of whatever alkoxide you're using is the same portion of the ester in this case. So if we look at a mechanism that we see here, and how all of this works, it's pretty similar to the aldol addition reaction that we just previously discussed. And I'm going to deprotonate this, form the enolate. And once I form my enolate here, this guy can now go and attack another carbonyl. And in our case here, it's going to be another ester, the same ester that we already have. Okay, so now we can see that if we push these arrows back down, let me go ahead and go on and attack the carbonyl here. Now what we're going to see though is something a little bit different, whereas in the aldol edition we didn't have a leaving group. Now we do, because notice that we're in our base is a methoxide. Well, the ester that I have would kick out a methoxide, so now I have a leaving group. So let me just draw this guy. There we go. So there you can see the leaving group. So now this oxygen can now kick back down and actually kick out or expel the methoxide, because I already have methoxide in solution. So we can kick this guy out. And now I form a carbonyl. And there it is. That's the product of the reaction, which is the beta-keto ester. And I now have this guy here. Now, just like we could do a mixed aldol reaction where we have different aldehydes or ketones that are going to react, we can do the same thing with a Claisen reaction. So we can do a crossed Claisen reaction. So as an example, here we have this ester, and in this case we're going to use LDA here because I'm going to completely deprotonate this. Or completely enolyze the one, and then I'm going to add my other guy. So here's my other ester. And again, we're going to want to add this slowly, just like before. So I'm going to completely enolyze the one, and then once that's done, I'm going to add slowly the other one that I wanted to add to, because I want to make sure that it doesn't get deprotonated at the alpha carbon. Then following our mechanism, you can see that we end up with, again, our beta-keto ester. So ketones can do this too, and ketones form beta diketones when you do this. So let's just look at an example of that with a ketone. So if I take this guy, we'll go back to cyclopentanone again and treat this with LDA. To give us the complete enolization of this. And once this is completely enolyzed, I'm then going to allow it to add to the other ester that I want. And of course, at the end of the day, I'm going to want to work this up with some acid. And there you can see that now I have my beta diketone with this once it happens. Aldehydes, of course, can do this too. So let's just give you an example here of this.
Eat your papers.
Can you show me your party papers?
So here, notice that the ester that I have has a methoxy group on it, so I'm going to treat this with sodium methoxide. And this will be sort of part number one and then I'm going to treat this with some acid to work it up. And there you go, you have your alpha beta ketoaldehyde in this reaction. Okay, so the next aspect that we want to talk about, so we've talked about all of these different reactions in which we are reacting with a molecule that is in an intermolecular fashion. In other words, that is from one molecule to the other. But this can also happen intramolecularly, in the fact that if it is intra, the intra means within the same. So we can do this basically within the same molecule, and we can actually form rings doing this as well. And so this works best when you're forming a 5 or 6 membered ring. And the 5 membered rings are actually made from a 1,6 diester. And then 6 membered rings are typically made from basically 1,7 diesters. And again, this really doesn't work any better for other size rings. You're looking really at 5 and 6 membered. So you're looking at the sort of, if you see a reaction, you're looking at this from, you want to count to see if you have either 1,6 or 1,7 diesters, and then basically you can see that you're going to do this in an intramolecular fashion, and this would be called the Dieckmann condensation if that is in fact what happens. So here's an example on how it works here. You can see that we can count all of the carbons, and so we're going to add one more here. Treat this guy here with our base. Notice again, I'm going to treat it with a sodium methoxide because that's the actual ester that I have, the OCH3. That's what I'm going to treat this with as a base. So just in case it hydrolyzes it, it doesn't really make a difference, right? I'll put that right back on there, the same group. Okay, so now this is going to enolyze. And I'm just going to kind of redraw this with the enolate here. I'm going to kind of draw it a little bit funky, just a little bit more so that you can see it. So here's my enolate, and so now you can see that this guy can kick back in, and those electrons can go and attack the carbonyl carbon, kick up the oxygen there. And once this happens, if you count the rings, or the carbons on the ring, you'll see I have a 5-membered ring. And I have a negatively charged oxygen that's up there. So just count your carbons there. And I shouldn't have drawn that like this, but oh well. That's actually a carbonyl, somewhat. And then these electrons kick back in, kick out my methoxide.
Tight.
A little tighter.
So just keep that in mind as well. So here's my ester, and there you go. You can see that now I have the cyclic structure there. This is my 5-membered ring product, and this was from a 1,6 diester. So when you see a diester and you're treating it with base, That's what you should think. Alright, so the last little bit here that we're going to talk about, the last sort of reaction, and there are more actually. You have like Robinson annulation and others. Hopefully I'll get to that in a different post. But for now, we're going to sort of end with what we call the Michael reaction. And this reaction itself works best when you have enolates that are made from beta dicarbonyl compounds. So let me just give you an example here. So notice this is a beta dicarbonyl compound because I have some carbonyl on either side, left and right, of the alpha hydrogen. So if you look in the middle there, that alpha hydrogen is way more acidic than a normal alpha hydrogen because on the left and right of it, the carbon in the middle has a carbonyl there hanging off of it. So it turns out that if I take this guy, and you see that I have this double bond that's adjacent to my carbonyl here on my aldehyde that I just drew, well, I can deprotonate that because I'm going to deprotonate the one that's in the center, the alpha hydrogen that's in the center in between the two carbonyls that has a much lower pKa. I'm going to deprotonate that, and it can actually add in 1,4 addition to this new carbonyl. So basically, this is just like a 1,4 addition that you have already seen. And what you're going to notice is that it's going to add in 1,4 fashion here, and we're going to form a new carbon-carbon bond. So how does all of this work? Let's look at this. So here's my beta dicarbonyl. This happens to be a diester. So I've got these two hydrogens that are there in the middle that I've drawn out that are more acidic because they're in between two carbonyl carbons. So pKa of probably about 14 or so. My base is going to go and deprotonate one of these. So I'm going to form my enolate here at this point. And now I've got what I call a Michael acceptor, which is the one that has my double bond that I'm going to draw down here, this guy. This is what's going to accept the electrons from the enolate. So this is my Michael acceptor. And now you can see that the donor here, the one that has a negative charge, is going to go and add to this in 1,4 fashion. And then this is going to kick the electrons over and push those guys up onto the oxygen. So now we're just going to kind of redraw what we have here. Running out of room. And now these electrons are going to want to kick back down. They're going to want to pick up a proton. So we've got the conjugate acid of our base that's kind of left over here, this, which would be methanol in this case. And so these guys kick back in. These electrons that are in the double bond are actually going to pick up that proton, so I'm going to now form another CH2 that's right there. And so let me just kind of redraw it now as the product. And there's our CH2, and then we have our, of course, we have our aldehyde there at the end. All right, that's it. Hey, thanks for watching. Hope this helps, guys.